this simple demonstration, you'll see what happens to an MOV when it's subjected to a temporary overvoltage or a swell event. Using a transformer and a variac, we can take a 120-volt input and vary the output between 0 and 300 volts. We're testing an MOV rated at 150 volts. This is the most common MOV used on 120-volt based systems. By pressing the fire button, a timing circuit allows the displayed voltage to be seen by the MOV in 30-cycle bursts. 30 cycles is half a second. Current transformers are attached to an oscilloscope to detect when current flows through the MOV. A displayed current on the oscilloscope will tell us at what voltage the MOV starts clamping, when it actually starts working. Now we'll start testing at 150 volts. Since the oscilloscope didn't register any data, we can determine that the MOV did not clamp at 150 volts. The full extent of that overvoltage event was seen by the protected load. Now we'll increase the output to 200 volts. And again, the oscilloscope didn't register current flow from the MOV. The MOV did not provide protection. Now let's increase the voltage to 220. And now we see that the MOV is beginning to clamp the voltage. And we see the amount of current that flowed through the MOV as indicated on the oscilloscope. I'll reset the scope before the next test. Now let's increase the voltage to 240 volts. And as you can see, the MOV failed. So this test clearly demonstrates that surge protection devices using only MOVs are vulnerable to long duration events such as TOVs or swells. This was a 1/2 second event at 240 volts. So the choices seem to be: 1, selecting a surge protection device with a high maximum continuous operating voltage that will make it immune to most TOVs, but giving you in return diminished surge protection because it's letting higher TOVs through the line. Or 2, selecting an SPD with a lower MCOV that will limit more TOVs, but will have a greater risk of failure. But are these choices your only choices? This demonstration is very similar to the previous one, except for one difference. In this test, we'll add a selenium cell in parallel with the MOV. Current transformers are set up to detect current flow through both devices. The current levels will be displayed on this monitor. We'll begin the test by subjecting the MOV in the selenium cell to a 30-cycle TOV at 150 volts. And we can see that neither the selenium nor the MOV did any clamping at that voltage. The downstream equipment would see the full extent of that power quality event. Now we'll increase it to 170 volts. And as we can see on the monitor, there was no current flow through the MOV. It did not clamp and provided no protection at this voltage. However, the selenium cell has begun to clamp. It is now providing protection to both the MOV as well as the downstream equipment. Now I'll just reset the scope. We'll now increase the voltage to 200 volts. At 200 volts, we can see that the selenium cell is still providing protection, with 16.4 amps flowing through it. Let me reset the scope. We'll now increase the voltage to 220 volts. During our MOV-only test, this was the first voltage level where the MOV began to provide protection. With the selenium cell in the circuit, the MOV did not provide any protection during the event, but the selenium cell did, with 24.8 amps flowing through it. I'll reset the scope. Now we'll increase the voltage to 240 volts. Remember that during a MOV-only test, this was the voltage level that caused the MOV to fail. As you can see, the MOV is still intact and has no current activity because the selenium cell is providing all the protection during the TOV event. At 240 volts, the selenium had 32 amps flowing through it. Now I'll reset the scope before the next test. We'll now increase the voltage to 270 volts. 270 volts is well past the voltage level that caused the MOV to fail. As you can see, the MOV is still intact and has very little current activity. The selenium cell had 39.2 amps flow through it and has continued to protect the MOV and the protected load during the TOV event. Now I'll reset the scope before the next test. Let's leave the voltage right here at 270 volts and remove the selenium cell from the circuit. What do you think will happen when the MOV is subjected to a 270 volt event without the selenium cell? As you can see, when the MOV is subjected to the 270 volt TOV event without the selenium cell in the circuit to protect it, it fails. So you can clearly see that MOVs are not capable of surviving TOV events because as the voltage increases, the clamping current through the MOV increases, and it can't dissipate the heat fast enough. But CaPS provides optimum protection because the selenium provides a higher clamping current capacity and a larger thermal mass to dissipate heat. The selenium cell also has a lower clamping level, so it can provide protection against TOVs that the MOV doesn't even see.